One thing we can do with linear regression, or kind of a variant of linear regression, is polynomial regression. So this is an example of featurization, or choosing some processed version of our data we're given as input. So one thing we can do, if we have, let's say we have just a single observed variable x, we can construct a feature vector that has x, x squared, x cubed, and so on. If we do linear regression using this as our feature vector, we'll get a polynomial out. That is, our expression is going to end up being w1 times x, w2 times x squared, and so on. By this we can see that polynomial regression is actually just a special case of linear regression. You can do something similar, as we discussed last week, by adding cross terms. That is, if we have multiple observed variables, we can include as features x1 times x2, x1 times x3, x2 times x2 times x3, and so on. Polynomial regression, also very widely used. So here's just an example. If we try to fit this polynomial, or these data points using no polynomial features, we get this line that's a bad fit. If we add x squared as one of our features, now we're doing degree 2 polynomial, degree 2, because we have features up to x squared, x to the second power, and we can get this nice degree 2 polynomial fit. So polynomial regression, again, very powerful 1D regression method. Here's a strategy that can be useful when it comes to evaluating linear regression, especially higher order linear regression, like polynomial regression. So here we've produced what we call a residual plot. That is, we're plotting the residual, that is y minus y hat, that is the true y minus the predicted y, without taking the square of the absolute value. So we're looking at the sign as well as the magnitude of the error. This is the residual for the 1D polynomial, for the degree 2 polynomial. Now note that the linear regression model assumes that errors are distributed according to normal distribution 0 sigma squared. That is, it assumes that the noise is kind of unrelated to the values of the parameters themselves. So if we look at a residual plot and we see an obvious trend, you can see here there's a very clear trend where the errors start high, dip in the middle, and get high again. That's a good indication that there's something funky with the fit, and that this 1D polynomial isn't doing a very good job of fitting these points. Now notice that once we go to a degree 2 polynomial, we get what we want, which is that the errors are centered around 0, and it doesn't look like there's much of a trend, positive or negative, or in the size of the variance as a function of x.